Hello, my name is Yoshida, a JICA Energy Efficiency Specialist. Today, we will look at data visualization, making energy balance figures, and analyzing EE and C policies through energy balance. We'll start with an explanation of energy balance figures. The second is a demonstration of how to make energy balance figures using 3 cases. The third is how to visualize sector-wise primary energy consumption. The last and fourth is a demonstration of making visualized sector-wise primary energy consumption sheets. Making energy balance figures and visualizing sector-wise primary energy consumption are highly effective for formulating the energy efficiency and conservation EE and C policies of a country. I hope that this lecture will help you formulate functional and efficient EE and C policies. Now, let me explain basic topics of energy balance figures. I'm going to explain the following items. First, the purpose of making energy balance figures. Second, the structure of energy balance figures. Third, how to obtain data. Fourth, important notes for making and utilizing energy balance figures. Fifth, how to make energy balance figures, where I will explain the terms and structures used by the International Energy Agency, IEA, by utilizing their materials. Sixth, how to visualize sector-wise primary energy consumption. Seventh, other visual tools offered by the IEA, which are useful in practical settings. Lastly, eighth, I will provide examples of how to analyze and utilize information of energy balance figures. Let's start with the purpose of making energy balance figures, abbreviated to EBFs in this video. Obtaining a grasp of data is vitally important to functionally plan, implement, and monitor the EE and C policies of a country. First, you need to make data-based decisions regarding the sector to be prioritized, the kind of EE and C policy to formulate, and so on. Having said that, assessment is not appropriately conducted in most developing countries. So, we must start by using accurate energy data to prioritize the challenges accurately. The IEA possesses the energy data of many countries, so I recommend their proactive utilization. We need to look at the total flow of energy, from energy supply and conversion, including power generation and refineries, to final consumption. Then, we need to identify the issue for promoting EE and C, from supply to final consumption. The data-based assessments of the whole must be carried out to identify issues. However, the numerical information of the energy balance tables found on the IEA website cannot be easily interpreted. Visualization of the information makes it possible for government officials and others concerned to share an understanding of the energy situation and challenges. That's why an EBF is a very functionally useful tool for visualization and enabling a common understanding. Next, let me explain the structure of EBF. The table on the left is from the IEA. This is the 2018 data for Egypt. The IEA website has tables like this for many countries. When visualized, the table looks like the figure on the right. Numerical information cannot be easily interpreted, but visualization as a figure makes it easier to grasp the important points. The structure of the IEA tables and EBF are basically the same. The top part shows energy supply. Each supply item is shown side by side by fuel and energy source, and the total. The middle part shows conversion. Energy conversion mainly refers to conversion in thermal power plants, transmission and distribution, and conversion in refineries. The bottom part shows final energy consumption. The lower part of each sector shows the total final energy consumption of the sector. The upper part shows the breakdown by energy source. In addition, this EBF also shows conversion losses and other issues, as well as the types of energy that the country depends on. Let's use the example of Egypt to understand how to interpret an EBF. The top part shows energy supply. The unit is kilotons of oil equivalent, or KTOE. Primary energy supply, or PES, is 95,619. Of the PES, we can see that dependency on fossil fuel is more than 95%. In particular, we can see that dependency on natural gas is more than 50%. The middle part shows conversion. The thermal power generation efficiency in Egypt is high, with net efficiency at 41%. The global average is 30.4%, and about 42% in Japan. So the generation efficiency in Egypt is not so bad, and there's not much room for EE and C targeting power plants in Egypt. Transmission and distribution losses are 17.1%. The global average is 8.6%. So there is room for EE and C activities in this area. Past cooperation by JICA that improved the efficiency of thermal plants and developed transmission and distribution lines are defined as the energy efficiency promotion on the supply side. The efficiency at refineries is 80.9%. Since the global average is nearly 90%, we can see that there is also room for EE and C efforts at refineries in Egypt. Next, the bottom part shows final energy consumption. Total consumption is huge in the industry, residential, and transport sectors. Egypt largely depends on thermal power generation. Therefore, we must give consideration to generation and transmission losses and multiply consumption by about 2.9 to grasp the real amount of the primary energy used. Reflecting this, primary energy in Egypt is consumed in the order of high to low by residential, industry, and transport sectors. Another important point is the value arrived at by dividing final consumption, FC, by primary energy supply, PES. The value for Egypt is 64.2%. The value shows a macro view of the energy consumption efficiency of the country. The global average is about 69%. So, we can see that the total efficiency for Egypt is somewhat bad. Of the reasons for this low efficiency, the factors on the supply side are as analysed up to here. As you can see, to improve the total energy efficiency of a country, we need to focus on both supply and demand. It is essential to apply an approach to reduce the final consumption, conversion losses, and primary energy that can be seen through the EBF. I will explain how to visualize primary energy consumption by sector and identify the priority in a later chapter. Next, let me explain how to obtain data. Two sets of data are needed to make an EBF: an energy balance table and data on electricity generation by source. You can obtain both from the IEA website. If a country's data is not available on the IEA website, similar information provided by the country or obtained in the past can be used to prepare a table in the IEA format for use as the basis of data input. This is the IEA website, where you can find the energy balance tables. Clicking allows you to change the country and year. Here, you can see data by energy source. Of the many categories, the wind, solar, etc. category is a bit tricky. Geothermal and others may be included at times. In such cases, you must change the values in this table before use. The data in the table cannot be used as is to make an EBF. If there is a value in the wind, solar, etc. column, you need to confirm what generation sources are included. This can be done by looking here at the electricity generation by source on the IEA website. Again, you can select the data from the upper part of the page. This shows what kind of generation source is included under wind, solar, etc., which you could not see earlier. You can complete the EBF based on this information. If you confirm that geothermal or nuclear power generation is included, take due care because there are specific calculation rules for them. I will explain the rules later in the demonstration section. Now, let me explain the important notes on making and utilizing EBFs. Whether from the IEA or the respective country, there are often many cases in which there are some accuracy issues. So, when making and analyzing EBFs, we will not regard errors of between 10 and 20% as being an issue. What's needed is an understanding of the macro situation. Small inconsistencies will be disregarded when making EBFs. The IEA data used also has a category of statistical differences, so keep in mind that such errors are always present when making EBFs. Now, let me explain how to make EBFs. First, you must understand the IEA's basic rules and the terms used. You can check them in the IEA's World Energy Balances 2020 edition, Database Documentation. This is the latest at the moment, so we are using it for this video. Please note that you always need to refer to the latest version when you do this exercise. For example, on geothermal power generation efficiency, the IEA sets a global average of 10% as the common rule for energy balance tables. Similarly, nuclear power generation efficiency is set at 33%. Such rules are written in the document. The gist will be explained in my lecture, so there is no need to read the full document. For the sake of efficiency, you can use an already made EBF as a model and change the values when making your EBF. Using a country whose supply and demand situation is similar to the target country as the model will enable smooth conversion. Let me show you 3 typical examples of countries to use as the model. This is the EBF of the Dominican Republic. The Dominican Republic is appropriate as a model for countries with a standard energy consumption structure. It is simple as a whole. It includes all components, from supply at the top to conversion in the middle and final consumption at the bottom. You can make an EBF by changing the respective values shown here to values of the target country. This is the EBF of Uzbekistan. If a table includes heat plants and/or combined heat and power plants, CHPs, the use of a Central Asian country like Uzbekistan as the model is appropriate. Cases like this that include heat and CHP plants, or with huge energy conversion losses, make the EBF making process a bit complicated. Next, if nuclear power generation is included, Pakistan is an appropriate model. As mentioned, the IEA sets nuclear power generation efficiency at 33%. So, be sure to reflect this when making the EBF. This template will allow the efficient making of an EBF. Let's take a step-by-step look at the EBF making process. First, look at supply, the top part of the IEA energy balance table. Type the total by energy in the lower part. In the upper part, type the values of production, export, and import. Here, biofuels and waste complicate matters a bit. In many developing countries, firewood, a typical biomass energy, is used in cooking at home. It is common to include this biomass energy for cooking in the energy balance analysis. However, it is reported that firewood is the cause of 3.5 million accidental deaths, a health hazard, and is accelerating desertification globally. This situation is encouraging many developing countries to promote a shift from cooking by firewood to cooking by electricity, or LPG. While the trend contributes to decreasing health hazards, it goes against GHG emissions reduction and EE&C. With this as the backdrop, firewood use at home is included in EBFs. However, when considering EE&C policies, please remember that firewood should be excluded as an energy source for the time being. In many developing countries, firewood is still often used by many households. So, make sure that you check this point especially carefully. Here is the summary of important notes for the top part. When considering EE&C policies, exclude firewood as an energy source. On nuclear power generation, use the efficiency of 33% set by the IEA for its energy balance tables. Regarding renewable energy in the category wind, solar, etc., check the energy sources. If it is wind or solar, set the efficiency at 100%. If the source is geothermal, apply the global average efficiency of 10%, as used by the IEA. If the IEA table contains values in rows below total final consumption in the lower part, categorize them as on-site power generation. Attention is necessary to these points in making the supply part of an EBF. I will explain this in more detail in the demonstration section. For the middle part, refer to the middle of the IEA table and copy the information to your EBF. There are positive and negative values. Negative values show input to power plants, refineries, and other facilities. Positive values show output from these facilities. As for refinery, include not only crude oil, but also energy sources used for processing in the energy industry own use row, that are oil products and natural gas as input. Copy and paste the value in the oil products column as output. As for power plant, include values in the heat plants, CHP plants, and electricity plants rows. Please note that you must show input and output of the hydro, wind, solar, etc., and nuclear columns in other parts, not in the part for power plants. You can use the values in the middle part of the table to check the values in the EBF. I will also explain this point later in the demonstration section. Next is final consumption at the bottom. Based on the IEA's energy balance data, type values by sector and energy. On-site power generation refers to solar power generation facilities at residences, etc. If the IEA table lists anything in the solar column, include it in the EBF. Now, let me explain how to visualize sector-wise primary energy consumption. Once an EBF is made, basic information on the energy supply and demand of a country is covered and can be used for discussions with the government. Visualization of sector-wise primary energy consumption is also effective for use in discussions with the government. This is an example of Egypt's detailed energy information. The top left chart shows values by sector and energy, copied from the final energy consumption values at the lower part of the IEA table. The bar chart shows that transport, shown in orange, seems to consume the most energy. However, we need to think about how much primary energy is needed for the electricity. When generation, transmission, and distribution losses are taken into consideration, the generation of 1 unit of electricity of the final consumption amount requires the input of 3.06 times that as primary energy. To grasp priority sectors for EE and C measures, decisions must be made going back to the supply side by looking at the total primary energy consumed, not at the sector's final energy consumption amount. This can be resolved using the table in the middle, which shows energy consumption by sector and energy type, based on the amount of primary energy. Tables show that 12,087 units of primary energy are necessary to make 3,950 units of the power used in industry. A broader view of primary energy like this shows that energy consumption in the residential and industry sectors is actually bigger than the transport sector. It shows something different from that seen in the final energy-based chart. The bottom right chart shows electricity consumption trend by sector, which is available from the IEA website. The analysis so far has been static. Since energy consumption structures keep changing, dynamic analysis is also essential. This is why these charts are there. In countries where national incomes are rising and car ownership is rapidly increasing, it is important for more appropriate EE and C to identify changes in the energy consumption structure across the years in order to identify priority sectors. When considering EE and C policies, priority must be placed on minimizing primary energy supply. A similar message was issued by the IEA in 2018. this is at the core of a country's EE&C policies. If EE&C policies are considered without this, you may not be able to reap benefits even after the thorough implementation of measures. Next is the example of Kazakhstan. This case shows big losses at conversion, such as in transmission, distribution, and transport. In such a case, there is room for EE&C not only in final consumption, but also in energy supply, which should be a target for consideration. Trends over the years show changes by sector. Although the amount is still limited, the residential sector and commercial sector, or buildings, in Kazakhstan are steadily increasing energy consumption in recent years. Please consider such trends when formulating a country's EE&C policies. Now, let me explain other visual tools offered by the IEA that are useful. First, let's look at energy balance flowcharts. Go to the IEA's website. Please note that the visuals of the IEA website are updated on an irregular basis, so follow the latest method to get the needed data. Click Data and Statistics. Next, click Access the Sankey in the lower part. This chart shows the global energy balance flow. The year 2018 is the latest at present. The left side shows supply by energy source. From the top, it's oil, coal, gas, biomass, nuclear, and other supplies. As the flow goes farther to the right, conversion takes place, with refineries at the top and power station at the bottom. The far right shows final consumption. So, in this chart, the rows and columns of the IEA table are transposed. The top right shows industry, then transport and other, which includes residences, buildings, and others. This is the structure. The left side contains the country list. For example, click Bangladesh, and you see the data for the country. So, this is basically how it works. This page shows the total energy flow from supply to conversion and final consumption. Please note that in the bottom part, years are shown. 2018 is the latest, though it's a bit small and may be hard to read. If you keep scrolling, you will see the changes in the flow of energy supply and demand over the years. There are other useful functions. Click Pie Chart. Click Power Station. You then see the breakdown of generation sources. Bangladesh mostly uses natural gas. It shows that oil products and hydro are limited as generation sources. Click the circle that indicates each pie chart, and you will see breakdowns. This is an example of a useful function. The second useful tool is the IEA's various energy indicators. They also show trends over the years. As we did before, click Data and Statistics on the IEA website. Then this page comes up. The left side shows energy topics. Energy supply is shown by default. Click here and you can select various energy topics, including CO2 emissions. All of them are topics. For example, select electricity and heat. The middle part shows indicators. The global information is shown now. Massive data is included here as indicators. For example, select electricity final consumption by sector. This is an example for the world. These lines may be a little hard to see. The right side shows graphic functions. Select area chart and you see global electricity consumption, which is used the most by industry, followed by residential and commercial and public services. Change world, for example, to Bangladesh. Bangladesh depends on industries, so its industry sector is rapidly growing. Its residential sector is growing fast too. We can see such changes here. We can see data not only for electricity, but also various other sectors. Next, we'll take a look at where to find information on carbon intensity. First, select key indicators in the energy topic. Then, in the middle, select CO2 emissions per unit of GDP, PPP. This is the global trend that shows that CO2 emissions per GDP in the world is decreasing. But if you look at Vietnam, CO2 emissions per GDP is steadily increasing over the years. Next is electricity generation by source for Vietnam. The line chart is hard to see, so change it to the area chart like before. Vietnam's electricity consumption is rapidly increasing at a steep curve. We saw that the CO2 emission is increasing in the country. The country depends on coal more than before. While the area of hydro is big, the country depends more on coal. So, one of the factors of the CO2 emission increase can be seen as its dependency on coal. There are various indicators like this. So, carrying out cross-cutting analysis using the various indicators should also be beneficial. The third effective tool is next. Again, click Data and Statistics. Click Access the Energy Atlas in the lower part. Here, click Topics. A massive amount of data is contained here, including coal, electricity, energy balance, energy indicators, natural gas, oil, and renewables. Such data is available here. For example, click Electricity Generation. Open this page. Scroll down to the lower part, and you see the trend of electricity generation by country in terawatt-hour over the years. The countries shown now by default are the United States and China, but the default changes on a daily basis. Let me type Bangladesh again. The consumption in the United States and China is huge, so I'll delete them. If you type Algeria, Bangladesh, Cambodia, or other country names, and look at the indicators, you can compare energy consumption by country over the years. This third tool is very effective for comparing countries and following their trends over the years. Now, I'll explain examples of how to analyze and utilize information of energy balance figures. This is the example of Uzbekistan. The top part shows circles indicating production in the country and rhombuses indicating import and export. Coal production in the country is 1,478. Crude oil production is 3,048. Natural gas production is 50,000. The energy produced in Uzbekistan comprises a large portion of its energy supply. Natural gas production is particularly high at 50,000. Its total primary energy supply is 46,000. We can assume that energy self-sufficiency in the country is high. To see its dependency on fossil fuel, look at the total, the lower part of supply at the top of the figure. Coal, 2,442, crude oil, 4,257, and natural gas, 39,000. These values show that more than 98% of the total primary energy supply of 46,000 is from fossil fuel. In the middle part of the figure, we see that electricity is provided not only from power plants, but also from CHPs. Likewise, we see that district heating is made available by both CHPs and heat plants. At the bottom part, electricity consumption must be converted to its primary energy amount. The conversion ratio is about 3. Multiply electricity consumption in red by 3, and you see that energy is consumed the most by the residential, industry, and transport sectors in that order. Also, we see that gas consumption in most sectors is huge. Making gas consumption in the residential sector efficient is especially a priority. Discussions with relevant parties using such information will enable you to formulate effective and functional programs. Next is the example of Jordan. The top part shows rhombuses indicating import and export. You can see that the values from trade are overwhelmingly big. For example, crude oil, 2,400. Oil product, 2,800. Natural gas, 3,600. These comprise more than half of primary energy supply, 9,100 at the leftmost. Overall, the country depends on imported primary energy by more than 90% of the whole. Like Uzbekistan, Jordan's dependency on fossil fuel, shown in the lower portion of the top part, is coal, 205, crude oil, 2,400, oil product, 2,500, natural gas, 3,400. Comparing these values with primary energy supply, 9,100, shows that the country depends on fossil fuel by more than 94%. Power generation efficiency, transmission and distribution losses, and refineries efficiency are about the global average. No major challenges here. The bottom final consumption part indicates that energy consumption in the transport and residential sectors can be priorities for discussion. We can also assume that in the residential and commercial sectors, on-site solar generation has spread to a certain extent. Next, let me explain threshold values in deciding whether there are big challenges seen in EBFs. Threshold values are shown in the table. These values are set with reference to those such as global averages from IEA data. Regarding supply, as with Uzbekistan and Jordan mentioned earlier, the points to check are import and export, dependency on import, or dependency on fossil fuel. One important point in the middle is the efficiency of thermal power generation. Considering global average efficiency at generation, the threshold level would be about 35%. Next is transmission and distribution losses. The threshold level would be around 10%. With regard to the threshold level for refineries, around 90% would be the one. Referring to global averages and other values as thresholds will help you make decisions in finding where the challenges lie. Next, let's look at the matrix of target sectors and countermeasures based on energy balance. First, the upper part is about the supply side. This part also includes thresholds such as a fossil fuel dependency of 50% and generation efficiency of 35%. If dependency on fossil fuel is, say, 50% or higher, the matrix shows that typical countermeasure candidates are for GHG emissions reduction, introducing renewable energy, and promotion of EE and C. Regarding transmission and distribution losses, there are two types: technical loss and non-technical loss. Technical losses arise from system-related electrical factors. A typical non-technical loss is electricity theft, which is particularly common in developing countries. Technical losses can be tackled effectively by renewing facilities and supporting improvement in maintenance capabilities. Distributing or promoting smart meters are effective against non-technical losses. The lower tables show demand-side measures. If energy consumption is huge in the industry sector, introducing energy manager certification systems and loans for introducing energy-efficient equipment would be effective measures. Energy manager certification systems have been introduced and promoted in many countries, and ISO standards have been set up. It provides some guidelines as well as makes it mandatory for massive energy consumers like factories and large-scale offices to efficiently manage energy consumption. Effective measures shown in the matrix for high electricity use in the residential sector are to introduce a labelling system, high-efficiency air conditioners, and LEDs. If EE and C in the transport sector is the priority, an effective measure is to reduce CO2 emissions through the promotion of electrification. These methods include a modal shift from gas cars to electric cars, or mass transfer, or a combination of electric cars and renewable energy. In Japan's transport sector, regulations have been introduced targeting logistic companies and large-scale business operators who place orders for the transport of commodities. Japan and Europe have been making great efforts to enhance automobile fuel efficiency, with moves to reduce energy consumption and the CO2 emissions of private automobiles, buses, and trucks. Please refer to these tables to identify effective and functional support measures. A concrete example of the use of EBFs and primary energy consumption assessments is this record of discussion, RD, with the Egyptian government on JICA's Technical Cooperation Programme for EE and C in Egypt. It contains priority sectors and energy sources based on analyses using these tools. The agreement stipulated the priorities based on quantitative data and made clear the actions to be taken by JICA and the government of Egypt. Also, the document includes analyses, such as a comparison of the current state of priority sectors, and the level of EE and C that can be achieved in the future through the project. This is a list showing the effect of introducing promising EE and C technologies, alongside primary energy consumption by sector. This is an attachment to the RD that shows primary energy consumption by sector, the supply-side values. They are multiplied by the expected EE and C rate, which is based on our experience in the introduction of EE and C measures. The results for sector-wise EE and C potential and the effect on primary energy reduction are shown in the table, The importance of regarding 1 kilowatt-hour of electricity as being the equivalent of 2.6 kilowatt-hours by converting it to energy input to power plants was confirmed prior to the record of discussion signing. I have explained how to make and utilize EBFs. Please use the EBFs on as many occasions as possible so that you can formulate effective and functional policies. Let's now start the demonstration of making 3 different types of EBFs. The first is the standard type. The second type includes heat plants and CHP plants. The third type is slightly complicated and includes nuclear power plants and so on. We'll start with the standard type. We'll use the Dominican Republic as the template to make the EBF for Vietnam. Start by changing the name from the Dominican Republic to Vietnam. Next, enter the supply part at the top. Next, enter the final consumption part at the bottom. Next, enter the conversion part in the middle, and check the calculation to finish the process. On the IEA website, go to Data and Statistics. Find the Data Tables tab and click it. You'll see balances, World, and 2018. Change World in the middle to Vietnam. You're looking at an energy balance table. The columns are for energy sources such as coal and crude oil, with total at the far right. The rows go from production, imports, and exports to TES. This is the supply part. The middle part, from transfers to losses, is conversion data. The bottom part, from total final consumption onward, is final consumption data. First, change the country name from the Dominican Republic to Vietnam. Also, change each of the values for the supply part at the top to those of Vietnam. Start with the total value for primary energy supply, PES. In the IEA's table for Vietnam, go to total energy supply at the far right, 83,455. Next is coal, 36,740. Change values from the left. Next is crude oil, 12,937. Copy the values from the IEA Energy Balance table from left to right. Next, for hydro and renewable energy toward the right. We can basically calculate the scale of RE as the sum of the IEA tables hydro 7,233 and wind, solar, etc. 45. Please note, however, that you need to identify what is in wind, solar, etc., such as geothermal. To identify this, click Data Browser. Select Electricity and Heat from the far left. Select Electricity Generation by Source in the middle. When you change to the area chart to make it easier to identify, click and look closely. You'll see the value for wind. It indicates that the representative RE is wind. I should note that the huge amounts of solar energy generation introduced from 2018 in Vietnam were not reflected in the IEA data used for making this video. This is not considered as an issue for this video, since its main objective is to explain how to create an EBF based on IEA data. As such, we are proceeding under the assumption that the data is complete. Going back to the main topic. In the case of wind, primary, secondary, and final consumption are the same. So, the sum of 7,233 and 45 is 7,278. This is the value to enter under hydro and RE. Next is electricity trade. The value is 85, which is imports of electricity. 148 subtracted by exports, 63. There is more import than export, so enter 85, the difference. For these two red parts, hydro and RE, and electricity trade, it's important to remember that you will need to refer to different places to get the values. Next is breakdowns at the very top. Circles indicate production. Rhombuses indicate trade. The first is coal. The IEA table shows 23,735 under production. Imports are 11,712. Exports are 1,360. The minus sign indicates export. Other parts, hydro and RE, for example, correspond 1-to-1, so keep the same number, or 7,278. For electricity, trade, enter the 148 and 63 from earlier. At the very top, type in the values with a circle for production, or with rhombuses for trade. Check the direction of arrows. This completes the supply part conversions and entry. Next, to the bottom, or final consumption. Here, again, start from total on left and check the values in order. Enter 60,273 to total at bottom left. Enter total values by sector, 32,545 for industry. Likewise for transport, residential, commercial and public services. The total value for agriculture onward are entered in others as the sum of 1,255 and 1,479. Next, energy consumption by type. The final consumption of coal is 14,172. Enter 14,172 to total final consumption. Oil products, 20,750. Natural gas, 985. Biofuels and waste, 8,083. Electricity, 16,284. Enter the values to the total final consumption row. Next, by sector, such as industry. It's shown by color. Grey for coal, yellow for oil and blue for natural gas, red for electricity and green for biofuels. Enter each value. For industry, coal is 11,795. Oil products is 4,618. Enter each of these values. If a fuel type changes, change the color of the arrow and the fuel type accordingly. The ratio between total final consumption and primary energy supply is the ratio between final energy consumption and primary energy supply, and an indicator of a country's energy efficiency. Calculate and enter 72.2% in this case. This completes changing the values of final energy consumption at the bottom. Lastly, move to the middle, the conversion part. We will primarily focus on two rows: electricity plants and oil refineries. Total final energy consumption for electricity is 16,284. The row before this is losses. This shows transmission and distribution losses, so enter 1,266 as loss. Calculate the loss rate of energy going to final consumption, 1,266. That's 1,266 divided by the sum of 1,266 and 16,284, which is 7.2%. Now check your calculations. Power plant here is for thermal power. Hydro and RE are already specified at the top. So calculate the output from only thermal power. This is the sum of total final consumption of electricity and losses, subtracted by electricity from hydro and RE and imported electricity. That is 16,284 plus 1,266 minus 7,278 minus 85, which equals 10,187. Enter that as the provisional figure. Next, look at the electricity plants row in the IEA table. Enter the energy input to thermal power plants. Negative values indicate energy input. Coal input to power plants is 22,567, oil input 65, natural gas 6,885, and biofuels and waste 52. Enter them as input. A calculation check can be performed now. Electricity output from power plants in the IEA table is 20,717. Subtract electricity from hydro, wind, solar, etc., which will leave only electricity input to thermal power plants. Also subtract the energy industry own use value, the electricity consumed by power plants. This will result in the value for energy output from the thermal power plants. That's 20,717 minus hydro, 7,233, minus wind, solar, etc., 45, minus energy industry own use, 522, which equals 12,917. Note that 12,917 differs by 2,730 from the 10,187 that was calculated earlier. But the IEA table shows a statistical difference of 2,731. This matches the 2,730 difference in our calculation for the EBF, assuring us that our calculation was correct. If there are no statistical differences, or it is zero for electricity, then the two calculations may differ by almost one or be the same. Statistical differences are sometimes huge. Be sure to keep an eye on the statistical differences row. Lastly, divide the output of power plant by the total of input, such as coal, oil products, natural gas, and biofuels and waste. This rate is called net efficiency. Calculation shows that the net efficiency here is 34.4%. The last is refinery. Look at the oil refineries and energy industry own use rows. The IEA data for Vietnam has no values for energy industry own use, so enter 10,991 under refineries crude oil. Enter the output of oil refineries, and 10,217, the output in the lower part. Calculate the ratio and get 93%. The conversion part is now finished, as well as entry and confirmation of power plant and refinery net efficiencies. The Dominican Republic was used here as the standard model to create an EBF for Vietnam. The steps for making a simple standard EBF for a country are: change the values in the supply part at the top, then the final consumption part at the bottom. Lastly, change the conversion part in the middle. Check the calculation in the middle part and complete the procedure. Now I'll demonstrate how to make an EBF when it includes heat plants and combined heat and power plants. Here we'll use Uzbekistan as the template for Mongolia. Start by changing the country name to Mongolia. Then go to the supply part at the top. Final consumption at the bottom is next. The middle conversion part is last. This part is complicated. This has heat plant, combined heat and power plant, and is the most complicated part as compared with other cases. First, change the top part, in addition to changing the country to Mongolia. Change the values of primary energy supply, such as the total values of respective energy sources. And change the values of production and trade. This is the figure after changing those values. Next is the bottom part. Enter the values on the IEA table at the very bottom, from left to right. The difference from the standard case is that there is heat, 1064. Enter this value from the total final consumption row. The last is the middle part. Uzbekistan is the most complicated case that includes heat plant. But Mongolia only has electricity plants and CHP plants, so enter values for them only, as follows. Transmission and distribution losses, 75. Calculate the loss rate. That's 75 against the sum of 555 and 75, a loss rate of 11.9. Next is this red middle part. Calculate the electricity outputs of CHP and power plant. From 555 plus losses, subtract hydro and RE, 39, and subtract trade, 141, which equals 450. The sum of 428 and 22 is 450. So, then, how did we get the 428 and 22? First, this 64 from electricity plants is total electricity output, of which 32 is from wind, solar, etc., and 7 is from hydro. So, take the electricity output, 64, and subtract 39, the sum of wind, solar, etc., and hydro, which equals 25. So, electricity output of electricity plants is 25. Electricity output of CHP plants is 498. The electricity output from CHP plants is larger than that from electricity plants. Using the ratio between these, 25 and 498, allocate the value of energy industry own use, 73. Then you get a breakdown of 3 for electricity plants and 70 for CHP plants. Subtract 3 from the electricity output of electricity plants, 25, to get the 22. For CHP, it's 498 minus 70, which equals 428. The equation from earlier was 555 plus 75, minus 39 minus 141 equals 450, and we have confirmed the earlier value for electricity. Next, for electricity plants, oil products input is 99. Enter this. Against this input of oil products, the output is 22, so the efficiency is 22.2%. The values of CHP plants, coal 3,197 and oil products 3. Enter them. Then calculate the loss ratio. 49 is divided by the sum of 1,064 and 49. The ratio is 4.4%. Also, calculate heat efficiency based on the energy balance table. First, heat from CHP plants is 1,250. Heat consumed in energy industry own use is 61. 1,250 minus 61 equals 1,189. Add the values below, 1,064 and 49. The total is 1,113. It is different from 1,189 by 76. On the IEA table, the statistical difference of heat is shown as 76. That means that the statistical difference matches. The calculation for heat has been confirmed. Also, calculate the efficiency of CHPs. CHP's output energy is the sum of heat and electricity. Divide this value by the energy input. This shows that the efficiency of CHPs is 50.5%. If there are any matters to note, it would be better to include them on the EBF. In particular, losses for coal is 252. This is a large amount compared with the 929 of the total final consumption. Make a note of the losses of 252 as reference. Make a notation here that a loss of more than 20% seems to be arising during conversion and transport. This will be useful later when identifying issues, formulating policies, and so on. This completes the process of using Uzbekistan as a template to make Mongolia's EBF. We have so far seen how to make an EBF that includes heat plants and CHPs. The key is the allocation of energy industry own use. Specifically, to allocate the value of energy industry own use according to the ratio of electricity output of electricity plants and CHP plants. Other steps are the same as in the standard case. Now, we'll move on to a demonstration of how to make EBFs when including nuclear and on-site power generation and others. We will use Pakistan as the template and change it for India. Change the country name. Change the supply part at the top. Next, change the bottom part. Then, change the middle part and check the calculation to complete the process. First, change the name to India. Enter total values by energy source. There's one point to note. The number here, 9,853, is for total energy supply of nuclear. IEA defines that 33% of this value is converted to electricity. So, the value to be entered as electricity here is 33% of 9,853, or 3,251. Be sure to remember this. There is no geothermal power generation in India, but if RE includes geothermal, calculate electricity output by multiplying by 10%. To identify the energy sources in wind, solar, etc., go to the data browser to see the specific electricity generation types. Although rare, the heat column in the IEA table can include solar thermal power generation. Even in such cases, only 33% of the primary energy supply is counted as electricity output. Such conversions are necessary when entering the supply amount from primary energy input at the top of the EBF. Aside from this, the handling of production and trade is the same as in other cases. Next, the final consumption part at the bottom. You need to note here that India has on-site solar power generation. In the IEA table, wind, solar, etc. contains 60 for industry, 801 for residential, 90 for commercial and public services, and 50 for non-specified. They are regarded as energy from wind, solar, etc. at the final consumption phase, primarily solar power, with power generation taking place at the final consumption phase. Include these values. There's one more thing to note. The total supply of wind, solar, etc., 9,946, is the sum of the total final consumption value, 1,002, and the electricity plant's value, 8,944. The top part of this figure shows a country's overall energy. It will help to show an arrow going from hydro and RE to the bottom part to indicate that the conversion part is skipped and the energy amount is generated on site. Other than that, the ways to specify sector-wise total consumption, sector-wise consumption by energy source, and consumption by energy source are the same as before. Now, let's look at the conversion part. First, enter transmission and distribution losses. Next, add electricity, 103,295, and its losses, 23,211, and calculate the loss rate of 18.3%. Furthermore, 103,295 plus losses, 23,211, minus electricity from nuclear, 3,251, minus electricity from hydro and RE, 22,941. Add 1,002, because on-site solar generation skips the middle part. Regarding electricity trade, the electricity is exported, so add 330. Add or subtract as appropriate, and record the result as electricity output from power plants. In this case, the result is 101,646. To check the calculation, look at the output of electricity plants on the IEA table, which is 136,132. Subtract electricity of nuclear, 3,251, which is 33% of the 9,853. Also, subtract hydro, 12,995. Wind, solar, etc., 8,944, and energy industry own use, 9,297. The result, is 101,645. The result in the EBF was 101,646, which is a difference of just 1 from the result using the IEA table. It is within the margin of rounding errors, so we will consider the calculation correct. Next is energy input to power plant. As in the other cases, look at the thermal power plants row. Coal, 234,969. Oil products, 4,178, and so on. Enter the energy input to thermal power plants by energy source. At this point, also calculate the efficiency, 30.8%. The last is refinery. Unlike the other cases, this is close to being standard. Input is crude oil, 270,754. Also, look at the energy industry own use row. It shows oil products 16,218 and natural gas 6,828. For input to refinery, oil products and natural gases are also sometimes used as fuel oil additives. So, enter these values in energy industry own use. The oil product output of oil refineries is 267,620. This ratio is calculated at the end as efficiency. This ends the middle part, completing India's EBF. This has been an explanation of making EBFs that include nuclear power generation and on-site power generation. The first point is in the case of nuclear. 33% of the primary energy supply is converted to electricity. If geothermal primary energy supply is included, 10% is likewise converted to electricity. In the case of solar thermal, 33% is likewise converted to electricity. The second point is to add on-site power generation output in the final energy consumption part. Also, going back to the supply side at the top, specify the amount of electricity supply of on-site power generation. Lastly, refinery. As in India's case, use as the standard the case in which input includes oil products or natural gas as fuel oil additives in addition to crude. Please keep these points in mind when making the EBF. Let's look at how to visualize primary energy consumption by sector. An EBF shows the overall energy flow. However, a disadvantage of EBFs is that the amount of primary energy consumed as electricity in final consumption is not shown clearly. Visualization of sector-wise primary energy consumption is very effective to make up for this as a tool to quantitatively identify priority sectors. Let's proceed. I will explain in 4 parts. First, the importance of primary energy-based assessment. Second, the structure of visualized sector-wise primary energy consumption sheets. Third, data input method. Fourth, examples of how to utilize the sheet. First, the importance of primary energy-based assessment. If a country depends on thermal power generation, 2 to 3 times more fuel is needed to make 1 kilowatt-hour of electricity. When considering EE and C policies, the desired approach is to minimize the country's primary energy consumption. In Energy Efficiency 2017, the IEA states that we should assess electricity consumption on a primary energy basis. So, the issue is, how can primary energy consumption be visualized? This is a visualized sector-wise primary energy consumption sheet. JICA has the template for this, but I will explain the overall structure so you can make one without the data file at hand. This is Serbia's case. First, sector-wise final energy consumption is at the top left. The data is available from IEA's energy balance tables. The corresponding figure is the one on the right. Please note that values have not been converted to those of primary energy. As a solution, the figure in the middle shows visualized sector-wise primary energy consumption, generated using the information from the tables at the top and bottom. The bottom part is for calculating the ratios of fuel for power generation against electricity. If CHPs or heat plants are present, sending the heat may require primary energy 1.2 times larger than the heat output, including intermediate losses. Here, primary energy that is 1.17 times larger than heat output is necessary. The primary energy needed for generating electricity is 3.24 times larger. Such calculations are performed here. In Serbia's case, the residential sector consumes more than 1/3 of the country's energy supply on a primary energy basis. It shows that the residential sector should be prioritized in EE and C measures. The bottom right shows trends over the years, which is the data available on the IEA website. It makes it possible to understand the trends at the same time. Prepare a template for data input. As with the EBFs, copy the data from the IEA table. As a template, complex cases like Serbia's that include CHPs and heat plants is versatile and appropriate. Most countries only have electricity plants, so calculation is very simple. The data that needs to be entered is shown in red. For other parts, once functions are set, automatic calculation enables the table and chart in the middle to be generated. First, enter sector-wise final energy consumption on the top left from the IEA table. Here, check to see that the total value in the IEA table is the same as the one in Excel. I will elaborate on this later in the demonstration. Next to enter is the bottom left, the generation multiplier. Please refer again to the data on IEA's table. There are 3 important notes. First, count the import of electricity as well as the on-site solar power. Second, include the on-site solar power and others in the power supply of EP. Third, subtract the heat supply value in the CHP row from electricity total in the table. I will elaborate on this later in the demonstration. Next is the trend on the bottom right. Enter the change in electricity over the year's data from a different part of the IEA website. Here, check the bottom right for the trend or type of power generation. When dependent on thermal, the ratio of primary energy consumption to final energy consumption is high. Serbia depends on thermal power, so the multiplier is about 3, as is the calculation result. The type of power generation is mostly thermal, so we can confirm that the data on this sheet is mostly correct. Briefly check the data like this. The last is the middle part, the core of this sheet. For electricity consumption, it's the ratio between primary energy consumption and final energy consumption. In Serbia's case, multiply final electricity consumption by 3.24. For heat consumption, use 1.17 calculated in the bottom part to multiply the final heat energy consumption and enter the value. Lastly, from coal to natural gases, enter the final energy consumption value as is. This process completes the procedure. Now, let's look at a JICA program that has utilized the sheet and see how it can be utilized by others in the future. First, when signing the RD for a technical cooperation program that started in 2020 for EE and C in Egypt, the calculation result in the middle part of this sheet was included in the RD's main text. This figure makes consumption by sector and by energy clearly visible. By sector, consumption by the residential sector is overwhelmingly large, followed by industry and transport. By energy source, you can see that consumption related to electricity is the largest. Oil consumption by transport is also not negligible. With such understanding of the big picture, we discussed which sector or energy source to focus on. It led to the formulation of an efficient, functional program in Egypt. The next example is the data used in developing an EE and C master plan for Bangladesh in 2016. JICA programs and cooperation with Bangladesh began based on this data. Bangladesh is an industrial country, and industry accounts for about 50% of energy consumption on a primary energy basis. The emphasized sector at the time of formulating the master plan was also industry. JICA later began a loan program for more than 30 billion yen for EE and C in the country, with industry as the main target. A master plan was prepared based on visualized primary energy consumption, leading to later incentives and loan program. Egypt's case was about visualizing primary energy consumption and making a chart of the calculation result of the middle part. There are other ways to utilize it. The table in the middle is modified to show the data in the order of primary energy consumption size by sector and energy source. This is the table. It shows that total primary energy consumption is about 40,000, of which about 23% is electricity for industry, followed by residential. The two account for more than 40%. It shows that the top priorities are electricity for industry and residential. In many countries, the majority of a country's energy consumption can be covered by picking up the top 5 energy-consuming sectors. In the example shown, the top 5 energy-consuming sectors covered 70% of the country's primary energy consumption. The next point is the electricity consumption reduction measures there are for reducing energy consumption in the industry sector or the residential sector. The energy efficiency and conservation potential based on our experience is that which is shown on right. EE and C toward the top energy-consuming sectors has the potential of reducing a country's primary energy consumption by 15%. We hope you can use such information to determine effective, functional support measures. This ends the overview of how to visualize sector-wise primary energy consumption and how to utilize the information. Now, I'll demonstrate visualizing sector-wise primary energy consumption. We will use Serbia as the example. This is the completed 2018 version of the visualized sector-wise primary energy consumption sheet for Serbia. Here, the core information is in the middle. The values in red are primarily those that need to be entered. Setting the functions enables the automatic calculation of the table in the middle and its generation as a chart. I'll explain where to obtain each data. First, final consumption by sector at the top. Columns are industry, transport, and other sectors. Rows are energy sources. To obtain data, go to IEA Data and Statistics Data Tables. Enter Serbia. Here we'll go to the bottom. This time we'll focus on final energy consumption. For example, power for industry 751. Power for residential 1153. Copy the data from the IEA table to the relevant spot. Here, we'll check that the total value in the IEA table and on the Excel sheet matches. In this example, it's 9,126 in the IEA table. The total in the Excel sheet is 9,125. The difference is within the range of rounding errors, so the consistency of the data is confirmed. This process has generated the visualized chart on the right. It shows that final energy consumption in the residential sector is large in Serbia. Next, go to the bottom left. This is power and heat from EP, CHP, and heat plants. Calculate the conversion ratio of primary energy consumption against final energy consumption. First, the red values need to be entered. Input energy for EP is 4,881. This is 2,161 plus 2,165 plus 550 plus 5. What is the source of these values? Serbia's case is very complicated. All three types of plants, such as electricity plants, CHP plants, and heat plants exist. The output from electricity plants is 2,161. Energy lost by conversion is 2,165. Imports of electricity is 550. The last value, 5, is from on-site power generation for wind, solar, etc. They are all the energy input involved in the generation of electricity. The total is 4,881. Next, power supply is 2,161 plus 5. The generation output from electricity plants is 2,161. That and 5 for on-site power generation combined is the output. The two values at the top have now been determined. Next is CHP's input energy, which is 992 plus 267 plus 1,930. Look at IEA's table. Electricity from CHP is 992. The value of heat is 267. And losses in conversion are 1,930. Their total is the input energy for CHP. Enter the total value. Next is power supply from CHP. Enter the value for CHP plants 992. Regarding heat supply, enter 267 from heat in the CHP plants row. Next is heat plants. Heat generated is 597. Losses from conversion is 83. The input is the sum of 597 and 83. The heat supply is 597. Next is energy industry own use, which is the electricity used in power plants. Enter 362 from electricity in the energy industry own use row. Next is energy industry own use, heat for thermal plants. The heat column shows 52. Enter this. The last values to enter are losses of electricity and heat during transport. Again, the IEA table shows losses. 390 for electricity. 74 for heat. Enter these values. We'll now calculate the results of the entries. When calculating power generation efficiency, remember that a part of energy input to CHPs is used for heat supply. Energy is used effectively in such ways. Subtract that portion from the input value of 3,189 before calculating power generation efficiency. Next, the output as electricity supply is EP and CHP output, minus own use and transmission and distribution losses. The two ratios are the efficiency. Next, heat supply comes from both CHP plants and heat plants, with losses within the plants and from transport subtracted from it to give us the available energy. Calculate this efficiency. Divide the effectively transported energy by the sum of that value and obtain the efficiency of that entered as losses. In Serbia's case, efficiency of heat supply is 85.4%. If losses are included, only heat of 85.4 can be supplied from energy of 100. In other words, calculate 1 divided by 0.854. Next, electricity generation efficiency is 30.8%. 3 times more primary energy than the output is needed. Calculate this ratio between primary and final energy for electricity. The bottom row is just for reference. It shows the rate of total losses from plant's own use and transport against supply. Next, the bottom right shows the trend over the years. Enter the electricity trend data from a different IEA source. Click Data Browser. Select Electricity and Heat and select Electricity Generation by Source. Copy to the chart. One important point here is the chart at bottom right. The one at far right shows the energy sources of power generation. In this case, the country depends mostly on coal. 3 times as much primary energy is needed to generate final energy. This is not that far off. Use 3.24 as the multiplier when converting final energy-based power at the top of the table to primary energy-based power. Similarly, use 1.17 calculated at the bottom as the multiplier to convert final energy-based heat to primary energy-based heat, and enter the result. Next, for values from coal to gas, enter the final energy consumption values as they are from the table above. There is a very important point in making the middle part. It concerns biofuels. Regarding biofuels, it is thought effective when making EE and C policies to disregard firewood in the residential sector. So, delete biofuels from the middle table. For Serbia, a look at primary energy consumption shows consumption is large for the residential sector against final energy consumption above. Also, industry's contribution level can't be ignored. For transport and commercial in the top chart, commercial consumes much electricity, and the multiplier becomes 3 here. It implies that if you are going to focus on transport, you should also focus on the electricity consumed by commercial. Next, let's see how to apply this to evaluate EE and C potential by clarifying the top 5 energy-consuming sectors. On the right, you see the primary energy consumption amounts for Serbia, which are copied in descending order by sector and energy source on the left. The biggest is electricity for residential at 3,739. Followed by electricity for industry. Oil for transport is next. The top 5 account for about 75% of the total. Formulating measures targeting electricity for residential, industry, and building would be effective. Focusing on other sectors would not have much impact. The table on right shows expected sector-wise energy efficiency rates according to our experience. A possible EE and C of 20% in residential through efficient heating, cooling and lighting, for instance. About 12.5% is possible in industry through efficient cooling and lighting, and 30% in transport through multiple measures. A possible 35% for buildings through efficient lighting, heating and cooling. Focusing on these 4 sectors and implementing appropriate EE and C measures could reduce the consumption of primary energy by 16%. If sector-wise primary energy consumption is visualized, data is shared and discussions are held to prioritize sectors, you can eliminate the formulation of programs for sectors that would not bring good results. Time can be spent discussing focused programs for emphasized sectors and review what would be effective as next steps. I have so far demonstrated how to visualize primary energy consumption by sector. Using this tool would enable concerned parties to effectively discuss the data and set priorities from a quantitative viewpoint. I hope you will utilize this tool. I have explained many things in this material titled How to Make Energy Balance Figures and a Data-Based Analysis Method for EE and C Policies. Of importance is how you utilize the EBFs, as well as the visualized sector-wise primary energy consumption sheets. Please utilize these tools to formulate impactful programs or to conduct more efficient monitoring activities.